Hello everyone, my name is Jaramillo, and today we're going to talk about the story of fossils. What are fossils? How did they get there? That's what we're going to be discussing, and I hope that I can bring you guys closer to a greater understanding of this. What are fossils, and how are they created? Fossils are the preserved remains of living organisms that died in the distant past. Fossils are incredibly significant as they are essentially a history of life. Due to the fossil record, paleontologists and evolutionary biologists are able to gain an understanding of how life evolved to become what it is today. Unfortunately, fossils are very rare and require a very specific set of circumstances in order for their formation to occur. And although many fossils have been found, it is estimated that we only know of 0.1 to 1% of the species that roamed this planet in the past. It's a lot of unknown history. Formation of fossils. The formation of fossils is very specific and occurs over a period of time no less than 10,000 years. It is uncommon for most organisms to fossilize due to all the events that must occur. This is why our fossil record is sadly so incomplete. First, the organism must die in or near water. Then the organism needs to be covered with a layer of sediment. This layer of sediment will protect the organism from rapid decay and from scavengers. Over time, the organism does decay to the point where bones, shell, or hard tissue remain. Minerals dissolved in the water are in constant contact with this hard tissue and saturated. As the intracellular and extracellular spaces of the organic material are infiltrated, organic minerals are dissolved and then replaced with inorganic minerals such as silica and other rock-like minerals. This results in a rock copy of the organism. Fossils and time. An essential part of our understanding of evolution is chronology of time. Without this understanding, our fossil record would simply be a fossil collection. Methods of radiometric dating are used to determine this time sequence. Radioactive isotopes all have characteristics of rates of decay. These decay rates are referred to as half-lives of that isotope. The half-life is defined as the amount of time it takes for half of the amount of a specified isotope to decay from its original value. These values can be calculated and a time can be determined for when the rock around the fossil was formed. Some half-lives are longer than others. For instance, the half-life of uranium is approximately 4.5 billion years, uranium-238 that is. And conversely, the half-life of beryllium-14 is approximately 4.4 milliseconds. Strata and the fossils within. Due to the fact that new sediment is constantly being deposited upon layers of older sediment, we can make a reasonable assumption that fossils found within a particular layer of sediment most likely lived in a similar or around the same time period to one another. This further gives us an understanding of chronology and is an essential part in the determining of evolutionary eras. For example, it would not make sense for a recent fossil to be found in the same sedimentary layer as prehistoric fossils. We can observe evolution through the fossil record. Scientists love patterns because patterns allow scientists to make predictions. One pattern that stands out in the fossil record is that many early organisms are less complex than their ancestors. That is to say that as time progresses, so does the complexity of these organisms. There are some exceptions, of course, but this holds true for many organisms and is one of the driving forces behind evolution. Anatomists have predicted that mammals have evolved from ancient reptiles, so it follows that we should find fossils that have reptile-like traits that were becoming more and more mammal-like with time. This kind of organism is referred to as a transitional form. There have been many transitional forms of organisms found that are quite bizarre. One of these bizarre transitional forms is shown right here. This is Pacacetus. In this photo, we can see an artist's rendition of the Pacacetus inachus, which is believed to be one of the transitional forms of the modern whale and hippopotamus. Wow. So we discussed transitional forms of animals, but What about the most important transition, the transition from a fish to animals that we see on land in the fossil record? That was a big transitional leap. It is understood that land animals came from aquatic animals, but there was a missing link that had yet to be discovered. Using the deductive reasoning of our understanding of sediment layers and time frames, it was predicted that this transitional form must come between 360 and 390 million years ago. This is due to the fact that lobe-finned fish are found in the fossil record 390 million years ago, but not yet terrestrial vertebrates, and similarly, terrestrial vertebrates show up in the fossil record 360 million years ago. So it makes sense that this transitional form would show up somewhere in between. In addition, the strata would have to have been created via freshwater, not marine sediments, because late lobe-finned fish and early amphibians both lived in fresh water based upon previous discoveries within the fossil record. In 2004, Tiktaalik was found, in precisely this environment and relative time frame. Tiktaalik was significant because it exhibited features that made it a direct missing link. Tiktaalik was a transitional form between land vertebrates and lobe-finned fish. Tiktaalik had a flattened salamander-like skull with eyes and nostrils on top. Tiktaalik also had both lungs and gills, and as well as a neck and stronger ribs to help with breathing air into its lungs. Tiktaalik had more robust fins with fewer bones that are similar in number and placement to land vertebrates following. The origin of the birds. Following our prediction pattern, 200 million years ago, birds are absent in the fossil record. 70 million years ago, birds are present in the fossil record. So birds came about somewhere in between. Perhaps one of the most notable among many transitional forms is the Archaeopteryx. Archaeopteryx was discovered in 1890 in a German limestone quarry and was first mistaken to be a small tetrapod dinosaur. This is because its skeleton was nearly identical to one. However, upon closer inspection, feathers were visible, and not just any feathers, asymmetrical feathers. This is significant because this is the characteristic that allows modern birds to fly. Archaeopteryx had a long bony tail, a neck attached to the back of its skull, a jaw, teeth, claws, and separate fingers on the wing. These were all traits consistent with dinosaurs. However, Archaeopteryx had feathers and an opposable big toe. Evolutionary biologists describe this transitional form as a mosaic, as it is halfway in between a tetrapod dinosaur and a flying bird. Here's some images of the Archaeopteryx. On the left, we see a fossil of the Archaeopteryx with feathers clearly shown. On the right, we see an artist's rendition of the Archaeopteryx. Here we have yet another artist's rendition of the Archaeopteryx. You can see that the various ancestors of the modern bird are all chasing a dragonfly. However, you can imagine that as if these various forms are chasing the dragonfly accompanied by the flapping of its wings or feathered arms, it can generate a greater running speed to catch up to the dragonfly. Similar to a swimmer who uses the water to pull himself forward with his arm motions. Even before flight, this would have been advantageous to generate land speed when chasing prey. It can be theorized that the forms with the greater, more rigid feathers were naturally selected for, and eventually running was no longer necessary. Fossil behavior. We can observe behavior in some fossils and compare that to the modern behaviors we see in various animals today. For instance, the nesting behavior that birds exhibit is shared by tetrapod dinosaurs and shows up in the fossil record. Another behavior, the roosting position that birds exhibit when they sleep, has also showed up in the fossil record with some fossilized remains of feathered tetrapod dinosaurs. You can see this in the image to the right. So what can we conclude from the fossil record? To conclude, evolution is systematic and relatively predictable. We have observed gradual change over time in the fossil record. We have observed transitional forms of organisms in the correct time frame and rock strata as we predicted. We can predict what traits these transitional forms should have had. We know that change is gradual and happens over time. We have observed changes within ancestral lineages as well as splitting from ancestral lineages. And finally, we have observed that future traits were based off of modifications of existing traits. This is all significant. This all shows us what fossils are, and it is a rock record of life on Earth. I hope that you have a greater understanding of fossils, and thank you for all of your time and attention.